All right, we're going to cover section 12.1. We're going to do a video that's a little longer than 5 minutes this time. It can be up to 15 minutes. When I'm at 15 minutes, I'll stop. I'm going to quickly review this section. Some of this section will cover examples that were done in sections 8.1 through 8.5, and therefore I don't want to redo them, but I wanted to review the concepts. So we have rational numbers a rational expression or a rational equation in this section, which are like rational numbers in the fact that they're a quotient of two things. But our quotient of two things this time are polynomials. And so just like a rational number, the denominator can't be equal to 0. And as a result, because the denominator can't be equal to 0, what we end up with are these things called restrictions. So we're going to take a look at the restrictions of a rational expression or a rational equation based upon kind of example here. So what we're going to look at is that we have f of x equal x squared minus 3 over x plus 9, and we're going to evaluate it at x equals 5. So this says plug in a 5 wherever we see the x, so we get 5x squared minus 3 over 5 plus 9. And then we simplify, so 5 squared, that's going to give us a 25, and 25 minus 3, which is going to give us a 22, and then 5 plus 9, which is 14, and then there's not much we can do with that except for reduce it, so I'll take this down by 2 in the numerator and 2 in the denominator, and that's going to give us 11 sevenths. And then, of course, we could change it to a mixed number, but I'm not going to waste my time here, because what we see here is a real number. Now, when we go to the second one, we're going to see something a little different happen here. So in this case, when we go to evaluate, we put in negative 9 here, squared minus 3, and that's over a negative 9, and then plus 9. And then from there, we're going to see negative 9 squared is 81. Negative times a negative is positive, remember. And 81 minus 3, that's going to give us, let's see, 78. And then from there, we'll have negative 9 plus 9, which is 0. And what we see is 0 in the denominator, that's division by 0. And remember, this is the instance that gives us an undefined. And undefined is not a real number. It's not a possibility. So this is a real issue. And that brings up the fact of what a restricted value is. So what we see is that when we look at a rational expression or a rational function, there are certain values that will make it become undefined, and therefore we should restrict those from the domain. It has nothing to do with what's going to happen in the numerator. It's only happening in the denominator. And so what we want to do is learn how to find the restrictions and get used to finding those restrictions at the front. So finding a restriction just means finding what will make the denominator of a rational function or a rational expression equal to 0. So if I want to find the restrictions of f of x equaling x squared plus 2x over plus 1 over x plus 1, I'm simply going to say, okay, well, what makes x plus 1 equal to 0? And I solve that really simple linear equation, and I find out that x equaling a negative 1 is what makes this equal to 0. Therefore, my domain of this rational expression, remember we a lot of times will write domains as d with a colon and then say that my x is such that, and that's such that my x doesn't equal a negative 1. And that is what my domain is. All real numbers except for a negative 1 is essentially what that says. Now on our second one here, we have a little bit more complication, right? This denominator down here can't be equal to 0. So when I come over here and I set this denominator equal to 0 to try to find out what's going to make it equal to 0, what I see is a quadratic equation or a polynomial equation of second degree, which means I'm going to use my factoring skills to find out where the zeros are. So I see that this has a leading coefficient of 1, so I'm going to focus on the factors of 10 that give me a difference of 3. So I have a 5 with a 2, and I'll have to have a negative 5 and a positive 2 because I need a negative 3. And now I take each of these and set them equal to 0, just like I was doing when I was solving polynomial equations of degree 2. And once I get that, then I solve these individual linear equations, and I find that x is equal to -2, and over here that x is equal to +5. And in this case, what I found is that my domain, and I'm going to write it in this little space right up here underneath the green one, we have that the domain here is all such x's such that x, and this time x doesn't equal two values, either, not a -1 this time, a -2, or a +5. And we can just write x doesn't equal to -2, 5, just like that. And those are the restrictions. All right, now moving on, the next thing that we need to look at is a value here where there aren't any restrictions. So when I take a look at this denominator in x squared plus 3x minus 10 all over x squared plus 5, the question is can I make x squared plus 5 equal to 0? Well, in order to make x squared plus 5 equal to 0, you'd have to make this equal to a -5, right? Well, there is no real number that when you square it equals to 5. So this isn't going to happen, right? And therefore, there are no restrictions on this domain. So remember, just because you have a denominator that contains a variable doesn't mean there are restrictions. It just depends upon whether you can make that denominator equal to 0 or not. So just keep that in mind. Now, moving along, we want to remind ourselves about a little fact here about fractions, that a negative numerator divided by a positive denominator is the same as a positive numerator divided by a negative denominator, which is equal to a negative fraction. And what we're going to see is that in rational expressions, this can happen here as well. So you see this numerator up here, 3 minus x over x squared minus 3x plus 2, that's the same as a negative fraction of x minus 3. And that's because here I took the negative x plus 3 that I'm actually seeing, and I factored out a -1, and from that -1 being factored out, then I got a positive x and a -3, and then I took this -1 and I put it out in the front. So we're seeing this whole thing. Now this could also have been incorporated down here in the denominator, so this could have also looked like x minus 3 over a -2 plus a 3x minus an x squared. And that's another way that this thing could have looked. So you see that there are many equivalent forms. So the long and the short of it is what I've written here, that the numerator or the denominator can contain a negative that can be factored out and used to rewrite as a negative fraction. So either this one where the numerator contains that negative or this one where the denominator contains that negative, it can both be factored out so that it looks like a fraction that is negative here. And we can use that quite often, and you've already seen me use an example like that, so don't forget about it. Right now we're going to review the fundamental principle of rational expressions, sometimes also called the fundamental theorem of rational expressions, which harks back to our fundamental theorem of fractions. It says basically if I have a p over q, which is a rational expression, if I multiply both the numerator and the denominator by some other polynomial that doesn't equal 0, then I'm going to get an equivalent expression. This allows us to build higher terms and reduce, just like it did with fractions. And here's a fraction example reminding you of what we did with that, and that's reducing. But we can also build higher terms that way. So now we want to review our simplifying of a rational expression. And simplifying a rational expression, remember, this just means that we're going to factor out the polynomials, and then we're going to cancel, and then we're going to rewrite. And when these things are a part of an equation, a function, right, make sure that you do find restrictions as well, and that's what that says in the written part over here. So I'm just going to take this one example here. I'm pretty sure we've done all of these examples within 8.1 through 8.5. But I'm going to take this one again and review the simplifying process. So what we want to do is we want to factor our numerator. Leading coefficient is 1, so I'm factoring the factors of 2 that give me a difference of 1. So I have an x and an x, because that's a leading coefficient of 1, and the factors of 2, there's only one set of those, so a 2 with a 1, and I need a negative 1, so that means I have a negative 2 and a positive 1. Now going down to the denominator, the same thing. I need the factors of 14 that give me a difference of 5, so I take an x and an x for the first factors, because that's the only way x squared factors, and the factors of 14 that are going to give me a difference of 5 are 7 and 2. I need a positive 5, so I need a positive 7, and I need a negative 2. Now once the numerator and the denominator are both factored, I cancel. One of these factors goes with one of these factors, and then I can rewrite this. This is x plus 1 over x plus 7. Now, if I were to find the restrictions on this, remember that I would have found the restrictions before simplifying, and the restrictions would be based on this. So this would mean that x cannot be equal to a positive 2 or a negative 7. Restrictions are always found before canceling, and that's what we're going to talk about with this next example here. This next example simply reminds us that that is the case. You can't factor, cancel, and then find your restrictions. So the question posed here is, why is it that for x equals 2 we get different results when evaluating x minus 2 over x squared minus 4 and 1 over x plus 2 when they're equivalent expressions? And you can see that they're equivalent expressions because if you factor this out, difference of two perfect squares, right, which factors into the sum and the difference of the roots, what we see is this one would cancel with this one, right? 1, and this is a 1, and so you get 1 over x plus 2, which means they're equivalent expressions. However, if we were to evaluate when x equals 2, in the first one I would get 2 minus 2 over 2 squared minus 4, and so what I would end up with is a 0 over a 0. And if you remember right, this is something called indeterminate. Now, indeterminate means that we can't determine what is going on here, and that is just as good as an undefined. It means that we have something that is of no value to us. Whereas over here, we have x being 2, we have that this is equal to 1/4. And so now we see that they have a value. Well, these are very different, right? But yet those are equivalent expressions, so we need to make sure that we find restrictions first, because even though they're equivalent, this one had a restricted domain that this one would not take into account. So this is just to point out the fact, find restrictions first before simplifying, right? So find restrictions first before you simplify. So find restrictions before you simplify. And this just points out the fact that it does make a huge difference. In one case, we get something that's indeterminate versus something that is a real number. All right, now moving on to the your turn problems. So here are the problems that I would like you to do for yourself, and then come back in the next video and go ahead and check those. And that one hopefully will be a very short video going over these few problems. Now I can't remember if these were done within the groupings in 8.1 through 8.3 or not, but I'm thinking they probably weren't. So these are probably some fresh new examples that you can challenge yourself with. So I'll see you in the next video that will go over these your turn problems.